So we will go forward and present the video of Professor Anis Koubaa from Prince Sultan University.
بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. First of all, I would like to thank Professor Eric Ferran for his invitation to present a talk in the KAUST Research Conference on Robotics and Automation. This is my second participation in this conference. I really enjoyed last year as well. And I'm glad and delighted to provide a talk on aerial systems for delivery and surveillance, trends, challenges, and opportunities. I'm Professor Anis Koubaa. I am full professor in computer science. And I am also the director of the Research and Initiative Center at Prince Sultan University, and also the director of the Robotics and Internet of Things Lab at Prince Sultan University as well. So content of my talk will be, first of all, I'm going to give a brief overview about our research lab, the Robotics and Internet of Things Lab. Then I will go through the different applications about aerial systems, both for delivery and surveillance. I will take you through an overview about the different applications that we have developed on aerial systems and also integrated with artificial intelligence. Third, I will present the different challenges to build commercial and industry level aerial systems. And finally, I will talk about the current opportunities in the drone market nowadays. So let me first give you a brief overview about the Robotics and Internet of Things Research Lab. The RIOT Lab is the first research lab established at Prince Sultan University and currently has 15 full-time researchers with different backgrounds in computer science, software engineering, electrical engineering, and mechanical engineering, working on multidisciplinary areas, including artificial intelligence, drones, mobile robots, Internet of Things applications, and emerging technologies. The lab focuses both on academic research and also innovation. The research lab has contributed to several innovation projects, including the development of a drone delivery system, face recognition platform, vehicle identification and license plate recognition, telecommunication tower inspection, and others, which we will discuss in this presentation. In this first part of the presentation, I will make an overview of the different applications that we have developed in the Robotics and Internet of Things Lab. Let me get started by the aerial survey applications. And as you can see from these slides, the global aerial imaging market size has been increasing since 2017, and it's forecasted that it will reach $4,125 million by the end of 2025. So this makes a compound annual growth rate of 14% every year. And here in the right side, you can see the distribution of the global aerial imaging market by drone platforms. And this was in 2017. So you can see that the fixed-wing aircraft are taking the largest share here. And in this case, they will use like vertical cameras. The second largest platform for aerial images are UAVs and drones, which are multi-rotor systems with 45.7%. And we have also helicopters with small share here in the green and other types of platforms with the red color here. Okay, so here in this slide, I'm going to take you through the different benefits of aerial surveys in construction sites. So first of all, it provides fast on-demand imaging process, so you can take a drone and collect images at any time for any area of interest. It provides accurate and high-resolution data because you can fly a drone at lower altitudes as compared, for example, to satellite images. It helps in reducing the costs and saving the time and improve efficiency. Like, for example, here in this mission that we've done in order to develop the 3D model and 2D model of the whole PSU campus, this just takes 1 hour of flight for collecting data. And finally, you can get accurate, high-resolution data, as you can see in a while. So another benefit is that the whole process is documented and it provides easier negotiation with subcontractor, especially if some companies would like to subcontract others in order to execute the aerial survey missions, and provide remote access to the construction site. So you can visualize at any time for a particular construction site the evolution of construction in a remote manner. So stakeholders do not need to move on site in order to check what is going on and what is the progress of the new construction building. So here in this mission, you can see our drone pilot Ryan and also Bilal Khawaf, one of the best graduate students who is very active in drones, have conducted this mission in order to provide the survey of the whole PSU campus. And at the end, we collect several images. I don't remember, it should be a couple of hundred of images, depending on the resolution required, depending on the accuracy that we would like to achieve. So the number of images that will be collected will depend from one mission to the other. And finally, these images will be processed by specialized softwares like, for example, Agisoft or Drone Deploy or Pix4D in order to generate high-resolution maps, either in 2-dimensional or 3-dimensional models, as you can see over here. So here in this slide, I show you one of the results that we have obtained from the survey mission, the new construction building. It provides very high resolution. This is like a 2D model that was generated from an aerial survey mission. And in general, the accuracy that can be provided can reach 2-3 centimeters horizontally and 5 to 6 meters vertically. So it's very high accuracy. And we can even increase the accuracy. As you can see, we can see all the details, even small things like on the ground. You can easily see them from this model. Now, this is a three-dimensional model. Using this three-dimensional model, we can even do measurements of the surface or the volume of particular area. And this can help, for example, in checking whether the construction is compliant with the planning that was done in advance. And even the accuracy can be improved further by using ground control points, which are landmarks that we put on the ground with known GPS locations. So here we use like RTK GPS in order to get the exact location with centimeter level accuracy of these landmarks. And these landmarks later on will be identified by the drone, and the software that we process the images will make an alignment of this landmark in order to improve the accuracy of the 3D model. So as you can see here, you can have measurements, for example, for particular areas or for particular segments. You can measure the area of a particular region here, as you can see, or for example, another particular region. And you can also measure the volumes. So plenty of things that we can do with aerial surveys in construction sites. Another achievement that we have done in the lab is to use aerial survey for telecommunication tower inspection. And this work was done in collaboration with our partner in the US, the GM6 company. So here, as you know, that cell towers need to be inspected regularly to ensure the strength of the cellular signals. And this operation is usually dangerous. So you can see here, employees has to climb the whole telecommunication tower in order to check the current state of the antenna, whether there is inclination, whether there is any anomaly, whether there is any defect. However, if we use drone, the process can be much easier and much flexible. And in the lab, we have used both drone combined with AI to make the process easier and automated. So instead of this tedious and dangerous manual process, we have developed a set of tools to make the cell tower inspection much easier. So here we just use a drone in order to get images from the cell tower. And finally, we use softwares in order to provide high resolution model of the antenna. Of course, this is much more complicated than aerial survey for constructions, because with constructions, you have big surfaces, but here the reconstruction of telecommunication tower is much tedious. So our AI solution is based on two steps. So first of all, we have a nested segmentation model using deep learning to automatically identify the antennas, as you can see. And second, we are going to use a reference antenna in order to measure if there is any transformation between the reference antenna and the detected antenna. And hereby, transformation, it can be an inclination with certain rotation or translation, and this will be considered as an anomaly that has to be fixed by telecommunication companies. So you can see here, it makes the process much easier and much more automated as well. Another work that we have developed also is to use unmanned systems for transportation system analysis, and in particular for traffic analysis. So we used AI to accurately analyze traffic from UAVs. So we combined AI and aerial images here. So we extract 24 types of information about the traffic. So we can estimate the speed of the vehicles. We can determine the number of vehicles crossing an intersection. We can also track the vehicles that circulate inside some selected zones, or to track the vehicle velocities and sizes over time. So we can extract plenty of information from aerial images using AI techniques. So here we are using object detection and tracking, and then we save all the information into a log file, and then we can make thorough analysis of the different type of information that you would like to extract. So as you can see here, we can generate different type of charts like heat maps for the average velocity per pixel, and other type of information as well, like the most congested area inside the road, or monitor the traffic intensity accurately over time. So likewise, we have also applied aerial images with AI to parking analytics, and this is a paper recently accepted in the Smart Tech conference that we are organizing in Prince Sultan University. It will be between 9 and 11 of May 2022 in Prince Sultan University. And for more information, you can go to this link of the conference. So here, the idea is to analyze the parking occupancy using AI and drones. So here we can extract, for example, the number of occupied slots over time. For example, here you can see how many slots are occupied, how many slots are empty, and all of these we use just AI tracking techniques. Also, in the same way, we are going to log all the information extracted, and then we will analyze them using some data science techniques to extract the number of cars occupied every slots, the occupancy of parking slots in second, and the number of occupied slots over time. So here in this demo, we have used the YOLO version 3 and deep sort in order for vehicle tracking. So for more information, you can refer to our paper that will appear in Smart Tech 2022. So another work that we have done is applied to agriculture sector. And in particular, we aim to count and also localize palm trees from aerial images. So as you can see here, we can make an automatic detection of palm trees, and not only detection, but also geolocation. And geolocation here, it's a kind of a complex process, because as you know, the accuracy of GPS devices can go up to 5 meters. And of course, localizing the palm at around 5 meters will not be efficient. So here we have developed a technique in order to combine multiple images that we collect, and we can generate several estimated points, and then we can make an average geolocation and we have reached an accuracy, an average geolocation accuracy of 1.6 meters. So the maximum error or the average error for the location of particular palm will be just 1.6 meters, which can be acceptable because usually the distance between palms can reach up to 10 meters. So one of our latest achievement is that we have developed drone for delivery, and we've made different demos for the Ministry of Health in 2021 and also for Saudi Post also. So the PSU delivery drone system provide a fully autonomous drone that is able to pick up a package from a particular location and then deliver it another location in a fully autonomous manner, as you can see here in this video demo. The features of our PSU delivery drone system: it has a smart magnetic gripper for autonomous pickup and drop off. We've developed software for fully autonomous package delivery and handling delivery missions, which supports autonomous package pickup and drop off. We have a maximum payload up to 5 kilograms, but currently we are around 2 kilograms and up to 30 minutes of endurance. The maximum range is up to 10 kilometers. And we have developed a fleet management system for managing the delivery operation of several drones with cloud support as well. So now the user can use a mobile app to place a mission to the cloud, and then the mission will be validated. And finally, after the validation, the drone will start execution of the mission. And we use onboard AI computer to enable the integration of onboard safety and security features such as object detection, obstacle avoidance. And the good thing in our system is that we use unlimited range. So unlike other systems that are based on telemetry, and telemetry is always limited in range, here in our case, we use the 4G and 5G networks in order to communicate with the drone at any time. So you can see in this demo, we have also developed precision landing. You can see there is a wind at the day of the demo, but the drone was able to land safely and accurately on the landing pad over here. This is the same thing. It's another demo that we have developed for the Ministry of Health for the transportation of blood sample. And of course, with the blood sample, we need to also maintain temperature, which adds an additional challenge. In this part, I'm going to present the challenges that are facing UAVs and their deployments. So let me first start by providing the challenges when you want to design a drone hardware. So basically, first of all, we have to identify what are the drone requirements. And the first thing that we think about is the endurance, how long a drone can fly. So usually we want that the drone to fly as long as possible. But of course, this is governed by the battery capacity. It's governed by the payload of the system that is being carried out, by the weight of the drone itself. So there are a lot of parameters that comes into play that will affect the possible achievement of the requirement. Also the payload, how much weight we would like to carry. So there is a balance to make between endurance, between payload, between also the range that the drone has to fly. So what is the distance that the drone can fly? This depends on the endurance, and as well, it depends also on the speed of the drone. And the speed of the drone depends on the motors that will be selected for that particular drone. So let me give you some frame options. Now, this is the Quad X configuration, which is quadcopter, and it has the advantage of being lighter weight. Of course, it will be lighter weight than, for example, these other configurations, simple in design and energy efficiency because it has only 4 motors. But of course, this type of drone usually they don't carry heavy payload, usually less than 1 kilogram. And it has limited endurance because here the battery, we will have to use a battery with lower capacity. And we can have a bigger scale, which is the Hexa X configuration. And here it has 6 motors. So it will provide 50% more thrust because we have 2 additional motors as compared to the quadcopter. It provides higher endurance because we can use bigger batteries. And it is more reliable due to redundancy. Here we have redundancy. So in the hexacopter, if one motor fails, the drone still can fly. However, in the Quad X configuration, if one motor fails, so the drone is going to crash immediately. Another type of drone is the octocopter, and this is the Octo X configuration. It has 8 motors, so it is used for heavier payloads. And this drone is safer than the 2 others because it can tolerate to lose the power of 2 non-neighbor motors. So, but here the limitation is that, of course, you have more motors, you have high energy consumption, you have higher weight, so the overall weight of the drone is going to increase, and higher cost. But of course, here it will be compensated by the fact that we can use more batteries. In some of the cases, octocopter, they can use even 4 batteries, even some hexacopter is going to show you in the next slides. As an example, this is an industrial level drone, which is known as the MFD 5000, and it allows different types of configurations. Here it is an hexacopter, so it has 6 motors, and this is a configuration that has a dry weight of 10 kilograms. So it uses 4 batteries, 6S, 8000 mAh, and the total weight of the batteries, as you can see, is 4.5 kilograms, and it allows to have a payload of 5 kilograms only. So you can imagine all these drones with this size, with this capacity, 6 big batteries, 4.5 kilogram of batteries is able only to carry 5 kilograms of payload, and the total weight is at 19 kilograms. So what would be here the flight time of this drone? Okay, it is estimated to be 17.1 minutes only. This is the estimated flight time with 20% battery capacity left for landing, because we need to have at least 20% in order for the drone to come back and land back at home. if we change just the payload from 5 kilograms to 10 kilograms. So in this case, okay, this configuration allows to have a payload of 10 kilograms, but this will affect the flight time. So we go from 17 minutes to only 12 minutes. Now, if we want to increase the capacity of the batteries in this configuration, all other parameters are the same, and we use 60,000 capacity and 4 batteries. So the total weight of the batteries, as you can see, it will increase to 7.93 kilograms. So adding capacity, it will add weight. So what you earn from the capacity, from the extra capacity, you will lose it from the additional payload. You have almost 3 kilograms of extra payload, which will be more burden on the drone when flying. So this configuration still, it's able to jump from 17 minutes to 27 minutes because we use the double capacity of the batteries. So in this diagram, and the source of the diagram is the MFD 5000 page, where it allows you to set different types of payloads, different type of configurations, and then it will estimate you the flight time. Of course, when we increase the capacity, the flight time will increase for the same payload. For example, if we take a payload of 5 kilograms, okay, we can jump from 17 to 27. And of course, if you use different types of batteries, you can see that you have also extra flight time. Okay, so this is the relation between the payload, the flight time, and the battery capacity. So, and you can see here for 10 kilograms, the maximum that you can get is only 20 minutes. And if you don't use any payload, as you can see here, so with zero payload, for example, with the 60,000 capacity, the drone can fly at 36.5 minutes. This is another graph that captures the relation between the flight time and the takeoff weight, again applied to the MFD 5000. So here in the x-axis, we have the total weight of the drone, or the takeoff, what we call the takeoff weight, and here we have the same type of curve. So the good thing in this graph is that we can know in advance what kind of configurations are not allowed by the regulation of unmanned systems. So as we know, for the regulation of unmanned systems, in order to be, for example, under Part 101 or Part 107, it should not exceed 25 kilograms of the takeoff weight. So for example, all these configurations in the red region are not considered eligible to work under the unmanned aerial system regulations. One of the problems that face the deployment of UAVs in the world is mainly related to regulations. As you observe from this world map regulation distribution, there is no standard regulation that governs the different countries in the world. Some of them have unrestricted regulations, like, for example, the countries shown in the green color. And some of them are fully banned, like, for example, the countries in the red colors here. But some of the countries that adopt regulations, they enforce line of sight deployment, but also allow non-visual line of sight operation for experimental purposes, such as, for example, in the US and also in Saudi Arabia. This is why it is very important when you drive an international drone business and operate drones over the world, it is necessary to understand that there is no one-size-fits-all regulation in the different countries, and that drone design and operation development must clearly be aware of the country-specific regulations. Now let's talk about the airspace challenge that is facing the UAV deployment. In this picture, we show the air traffic of manned system aircrafts used for traveling for cargoes around the world. We can easily see how huge the traffic is, but fortunately, it is well controlled with clear regulations and laws, and also it operates in the wide airspace. The deployment of UAVs is expected to exceed this traffic, and what makes it even more challenging is that it will share a much smaller portion of the airspace, which makes its operation a bigger challenge. Looking to the airspace classes, there is only one airspace that is uncontrolled, Class G, and all other airspaces are controlled and being used by the manned traffic and requires the ATC authorization, ATC for air traffic control. The UAVs are expected to be mainly deployed in the uncontrolled Class G airspace with the regulations already mentioned, and can also operate in other classes with prior and extra authorization. In this slide, we show the projection of drone operation from 2018 to 2023 for different types of drones. Recreational drones are expected to consume most of the traffic, with a projection traffic of 1.7 million drones by 2023 in the extreme scenario. The commercial deployment is also expected to be very high and may reach 1.2 million by 2023. The combined number of recreational and commercial drone is projected to reach 2 million to 3 million by 2023, which makes a huge expected increase of volumes of operations and service demands. An additional challenge is that a large portion of unmanned aerial systems will also operate in the beyond visual line of sight mode, without visual line of sight, given that these drones will be fully autonomous. For example, for package delivery, the drone will be fully autonomous, as we have already seen in the previous demo. This is why a UTM is a must to allow for the deployment of the UAVs. The FAA has started since a couple of years ago to design its UTM system, and these diagrams show its architecture and the main stakeholders, including the authority, which is the FAA, and Saudi Arabia we have GACA, the operator, which is the company operating the drone, the remote pilot in command, who is the pilot operating the drone, the public safety and general public, which helps in providing rules and regulations, and several services and supporting infrastructure agents, such as a UAS provider, which mediates between the authority and operator, and the USS network, which is the medium to exchange communication between the USS and operators, and the Flight Information Management System, which is developed and maintained by the authority as a portal to handle requests related to drones operations. And finally, the National Airspace System. In the RightWay Lab, we are also working on developing a UTM system very close to what was proposed by the FAA. So you can see here the interaction between the different stakeholders. We have US operators will be operating drones, and drone will be communicating with each other using V2V communication. And the US, when they need any information, they will not interact directly with the authority. So here it's the authority. They will interact with a US service supplier, okay, which we call USS. And this USS service supplier is delegated by the authority, which is the FAA in the US, and will provide constraints, requests for information, and for the US, so that later on they will provide it to the operator. And the US also mediates between not only operator and the authority, but also they mediate with public safety and other public agencies as well. And they can take extra information from supplemental data service providers, like, for example, weather conditions, terrain, surveillance, performance, and so on. So this is like the general architecture of unmanned traffic management system designed by the FAA. One of the most important challenges in the design of the UTM is to identify a particular drone with an ID. The FAA has developed the concept of remote ID, which is a system that must be integrated into the drone to provide them with a unique identifier in the UTM. FAA will impose remote ID on all UAS. All UAVs must comply within 3 years since the date of issuing the remote ID rule. The manufacturer cannot produce drones without remote ID compliance within 2 years after issuing the rule. The FAA remote ID applies to all commercial and recreational drones more than 250 grams. And there are 3 main categories of remote ID. We have the standard remote ID, which broadcasts remote ID over radio frequency rather than the internet to the FAA. Okay, so for example, here there is a drone, and the drone is going to broadcast its ID and will be captured by the public mobile phones. So there will be people that need to collaborate in this system with some special applications. And then through this mobile phone, the remote ID will be sent through the internet to the authority. So this is the way how the FAA has designed mainly the remote ID to work. They didn't rely on cellular networks, 4G or 5G communication. And the reason was because some rural areas, maybe they are not connected with cellular networks. The second category of the remote ID is what is called the limited remote ID. There is no broadcast, but must operate within 400 feet from the pilot controller. So here, if the drone flies in visual line of sight and below the 400 feet, 120 meters, then there is no need to broadcast the remote ID. And the third category is the FAA recognized identification area. It's a known area where the pilot can fly drones in visual line of sight, okay, without having to also broadcast the remote ID. These are the 3 main categories. So another approach that we have developed in the Robotics in Internet of Things lab, also to identify drones, we have developed a means to identify a drone using the Roslink protocol that we have started its development since 2017. The Roslink is a protocol that allows the communication between robots and drones over the internet. And we achieved recently a very advanced implementation of this protocol with advanced security features as well. Roslink also uses a system ID to identify a drone, and we use the 4G, 5G cellular network to remain in communication with the UTM in real time. So here, as you can see in the architecture, if we have a drone or VTOL, it will be broadcasting its system ID through a Roslink message. Of course, there are other information that will be also broadcasted. It will broadcast to the closest base station, either it is 5G base station or 4G base station. And then it will be communicated through the internet to the authority, and finally to the operator, and also to the end user. So in this way, we are able to monitor and track the operation and drones in real time. And also we are able to send any control command also through the internet, through cellular networks, 4G or 5G, to the drone, as we have already illustrated in the previous delivery demo. Other challenges that face drone deployment is the type of communication, which can be point-to-point network or also satellite communication. Cybersecurity is another very important issue that will be facing the beyond visual line of sight deployment of drones, and also has yet to be achieved in terms of ensuring authentication, confidentiality, availability, and integrity. One more challenge is the design of drones with multi-package capabilities. In fact, a single package delivery would not be efficient or cost-effective. There are even more challenges and opportunities to discuss, but considering the time limitation, I hope what was presented provided some insights about these challenges. Thank you for your attention.
Thank you. So for any question, we have Dr. Mohammed Abdul Qadir here. He's from Anis Koubaa lab.
I'm Mohammed Abdul Qadir from the Robotics and Internet of Things lab at Prince Sultan University. I'm also an alumni of KAUST. Unfortunately, Dr. Anis Koubaa couldn't make it today for sort of last-minute unforeseen circumstances, but we're very glad that we are here. Thank you, Professor Eric, and the organizing team for the quick arrangements. And I will try my best to answer your questions regarding the information that was mentioned in the presentation.
Okay, there is one question from the offline. It says that, has the drones been commercialized?
Yes, thank you for the question. We are actually in the phases of starting, business side of the products that or the prototypes or the engineering prototypes that we develop in the lab. So yes, it's in the plan. And also I have with me here Dr. Mohammed Al-Shail, who is the President Advisor for Business Development, who can answer more questions about the business development part.
How do the regulations differ between the US and Saudi Arabia in terms of drones?
Very good question. So as far as I know, there's no enforced regulations with regard to drone operations, commercial operations. In fact, we are working with GACA, which is the General Aviation of Civil General Authority of Civil Aviation, in order to cooperate with them to develop the regulations of commercial drones in the kingdom.
Thank you.